Imagine a blue, sunlit sea whose vast waters below survive with almost no oxygen. It resembles a dark box with a bright lid, even though the box itself has never truly been black. At its deepest point, the seabed lies more than 2,200 meters below the surface. Across many areas, familiar marine life is concentrated mainly within a thin layer near the surface. Deeper still lies an enormous oxygen-poor water mass containing dissolved hydrogen sulfide. By ordinary logic, a divided body of water like this should struggle to function as a living sea. Its frightening name makes people believe the water itself must be unusually pitch black. If the boundary between the layers disappeared, oxygen-poor deep water could invade habitats above. If too much organic matter sank, decomposing microbes would continue removing oxygen from the water. If water exchange weakened further, the deep layers would struggle even more to receive necessary oxygen. Yet above that boundary, fish still swim, plankton still bloom, and the waves remain blue. Along its shores, cities, ports, and fishing communities still live beside this seemingly impossible sea. The secret is not black water at the surface, but the locked silence hidden deep below. This is the Black Sea, whose famous name is far darker than the true color of its water. For thousands of years, it has faced isolation, stratification, and a deep layer unable to breathe. To understand the name, the Black Sea must first be seen as a basin almost completely enclosed by land. Unlike an open ocean, its water must pass through several narrow straits before reaching the Atlantic. Its nearest gateway is the Bosporus, a tiny corridor compared with the enormous water mass behind it. From the north and west, major rivers continuously pour fresh water into the basin. River water is lighter and less salty, so it tends to remain above deeper seawater. Meanwhile, saltier Mediterranean water slips through the straits and sinks beneath the surface layer. These two different water sources created the foundation for the sea's stable layered structure. That structure did not appear overnight, but formed through long geological and climatic changes. After the ice ages, sea levels and connections with neighboring seas changed dramatically over time. How suddenly those ancient changes occurred remains a subject of continuing scientific debate, but the final result is clear: a deep enclosed sea with only limited exchange outside. For ancient sailors, this geography was not a scientific diagram, but a journey filled with uncertainty. Unknown coasts, rapidly changing winds, and few shelters created an atmosphere of hostility. The Greeks once used a name often understood as meaning a dark, harsh, or unfriendly sea. One explanation traces that name to an ancient Iranian word associated with darkness. Another theory connects black with north in an old system that used colors for directions. These explanations compete, so the name's history cannot be reduced to one single cause. An older name was even softened into a meaning of hospitality, perhaps to calm fear of the sea. The name therefore records emotion and geography more than any measured color of the water. Geography created the first dark box, but human memory locked it shut with a name. Coastal communities did not wait for chemistry. They learned to read wind, waves, and the color of the sky. Blue-gray water before a storm became a practical warning, though it never explained the sea's name. Under clear skies, the same water can shift between blue, green, and silver. Near river mouths, sediment clouds the water and creates brown-green bands along the coast. In clearer offshore waters, blue light travels deeper before being absorbed and scattered. Fishers soon noticed that sea color changed with seasons, currents, and drifting microscopic life. But surface observations could not reveal what existed hundreds of meters below them. Early knowledge therefore focused on coastlines, storm shelters, and safe times to sail. Ports gradually transformed a sea, once feared as hostile, into a network of trade. Coastal routes reduced risk by keeping ships near familiar bays and river mouths. Accumulated experience helped people live with the surface, while the deep remained completely unknown. To measure depth, sailors once lowered weighted lines until they reached the seabed. Each disappearing rope became a slow, difficult measurement heavily dependent on weather. Mud samples sometimes emerged dark, but seabed mud was never the color of the entire sea. Deep metal objects can darken through sulfur compounds, inspiring additional folk explanations. Yet chemical marks on the seabed do not prove that the sea was named after them. Humans adapted to what they could see, but real understanding required instruments entering the water. When the first sampling bottle descended, the dark box began opening from within. Deep water samples revealed the smell of rotten eggs, a signature of dissolved hydrogen sulfide. From then on, the question changed from what color the sea was to why its depths could not breathe. Later expeditions turned isolated water samples into detailed profiles arranged by depth. Temperature, salinity, density, and oxygen were measured together to locate boundaries between layers. Modern instruments can record countless small changes throughout a single descent. Instead of one hard dividing line, scientists found several overlapping transition zones. The surface layer changes seasonally with wind, temperature, rainfall, and river inflow. Below it often lies a cold water layer formed and preserved through seasonal cycles. Deeper still is a zone where oxygen falls sharply and chemistry replaces familiar ecosystems. Beyond the transition lies anoxic water, where hydrogen sulfide gradually increases with depth. Depth maps show a shallow northwestern shelf and a broad, deep basin at the center. This means the oxygen boundary does not lie at exactly the same depth everywhere. Wind can mix surface water, but that energy rarely reaches the basin floor. Science must therefore measure not only water, but how each layer exchanges material. Surface currents carry heat, salt, sediment, and organisms around the coastline. Large eddies can trap or disperse material, creating broad changes in the sea's visible color. Satellites can see those color patterns, but they cannot directly smell or measure deep water. Research vessels fill the gap with water samples, sonar, depth instruments, and chemical sensors. Repeated survey routes reveal how the oxygen boundary shifts over time. Each measurement is like a thin slice through the box, revealing the position of hidden layers. Combined together, many slices create a three-dimensional picture of the entire sea. Monitoring also shows that surface color changes between spring, summer, and winter. Where sediment and organic matter are abundant, water often appears greener or browner than offshore. When plankton multiply rapidly, bright turquoise streaks can become visible from high above. Beneath thick clouds, the same water may look graphite gray because it reflects the sky. Visible color is therefore produced by light and suspended matter, not by the sea's name. Observation separated the story into two parts: color at the surface and chemistry below. Sea color begins with white light, which contains many wavelengths perceived as different colors. Water absorbs red light faster, while blue light often travels farther and returns to the eye. That is why clear seawater appears blue, even though individual water molecules are transparent. However, the Black Sea receives abundant river material, making its colors more complex than pure water. Tiny mineral particles scatter light, making coastal water appear pale and cloudy after heavy rain. Dissolved organic matter absorbs some blue light, gradually shifting the water toward green. Plankton cells both absorb and scatter light, producing changing bands of color. Waves alter reflection angles, so the same surface can flash silver and darken within seconds. Depth also matters because deep water reflects less light from the seabed than shallow water. The central basin therefore often looks darker, yet remains deep blue rather than completely black. The sea's true color is not one answer, but a range changing with place and time. The stranger story begins where light nearly vanishes and water density becomes the controlling force. Saltier water is generally heavier because dissolved salt increases its density. Less salty river water stays above, while dense southern inflow slides into the lower layer. The density difference acts like invisible glass, preventing the two water masses from fully mixing. Wind stirs the upper layer strongly, but usually loses energy before crossing the deeper density barrier. Atmospheric oxygen therefore enters mainly the water that contacts and mixes near the surface. Photosynthetic organisms also produce oxygen where light remains, but cannot function in deep darkness. Meanwhile, dead organisms and waste from above continue sinking into the lower water. Microbes decompose this material using whatever chemical electron acceptors remain available. When oxygen is abundant, decomposition uses it first because that pathway is most efficient. After oxygen disappears, different microbes switch to reactions suited for an anaerobic environment. Some bacteria use seawater sulfate and produce hydrogen sulfide as a final product. Hydrogen sulfide smells like rotten eggs and is toxic to many organisms at sufficient concentrations. In deep water, it does not form giant bubbles. Most of it remains dissolved. Its concentration usually rises with depth because bottom water renews slowly and receives little oxygen. A fragile chemical transition exists between oxygenated water and sulfide-rich water. There, sulfur-oxidizing microbes exploit compounds arriving from both directions. This boundary acts like a biological checkpoint, consuming many substances before they travel farther. Stable stratification keeps deep hydrogen sulfide from regularly reaching people at the surface. That stability protects the surface while keeping deep water oxygen poor for long periods. Fish, jellyfish, dolphins, and most large organisms therefore remain within oxygenated upper waters. Below that boundary, large animals give way to microbes adapted to extreme conditions. The seabed is not completely lifeless, but its organisms differ greatly from familiar ocean ecosystems. Low oxygen slows many decomposition processes that are faster where bottom animals disturb sediment. Organic material can therefore be preserved more effectively and accumulate as a record of the past. Deep wooden shipwrecks can remain astonishingly intact because wood-boring organisms cannot survive there. This is not magic, but the result of darkness, low oxygen, and little biological disturbance. The dark box becomes an archive, preserving carbon, sediment, and traces of history. Yet that preservation exists because most of the deep seabed sacrificed an oxygen-rich habitat. The habitable layer forms only the upper part of a deep basin, limiting ecosystems vertically. When oxygen declines in shallow water, organisms cannot simply dive deeper to escape. That makes coastal oxygen changes especially important for fish, fisheries, and shoreline communities. Rivers bring more than water. They carry nutrients, soil, organic matter, and pollution from land. Excess nutrients can trigger plankton growth, creating green water that appears healthy. When the bloom ends, dead organisms sink and become food for bacteria. Bacterial decomposition consumes oxygen, sometimes leaving shallow bottoms suffocating. This coastal oxygen loss differs from the deep anoxic layer formed over much longer periods. Confusing the two can make every Black Sea problem appear completely natural. Deep stratification is natural, but human activity can still weaken the living upper layer. Warm water is lighter than cold water, so warming can strengthen surface layer stability. A more stable surface can reduce vertical mixing and make oxygen harder to transport downward. The exact response also depends on winter cold, wind, currents, and yearly river inflow. A cold winter may mix upper waters more strongly, yet still cannot overturn the entire deep basin. The real concern is not instant overturning, but small changes accumulating over decades. Even a modest upward shift in the oxygen boundary can significantly reduce habitable space. On shallow shelves, that shift can reach the bottom and directly affect seafloor organisms. Fishers may notice fish changing location before underwater chemistry is clearly measured. What appears to be a change in catch may begin at an invisible boundary below. Coastal pollution also lingers longer because the Black Sea exchanges water slowly with the open ocean. Deep water is not a tank that can be quickly cleaned by opening a simple outlet. Crude interference with stratification could create unpredictable chemical and ecological consequences. Hydrogen sulfide inspires energy ideas, but the engineering and environmental challenges are extremely complex. Any plan must avoid lifting toxic water or disrupting a long-established balance. The true darkness is not the water's color, but the fragility of the living layer above. One calm morning, a research vessel stops over the deep blue center of the basin. At the surface, nothing reveals that an oxygen-free world lies directly below. A sensor frame descends carrying water bottles, oxygen probes, and salinity instruments. The first meters are filled with sunlight, bubbles, and plankton drifting in surface currents. Deeper down, red light disappears first, leaving a cold blue world with little contrast. Fish become fewer, not because they fear the machine, but because suitable habitat is ending. The sensor crosses the cold intermediate layer, a winter signature preserved beneath the surface. Then oxygen begins falling quickly while sunlight shrinks to a faint blue trace. The instrument enters nearly oxygen-free water, where large life disappears from view. Only a short transition can separate two ecosystems that are almost completely different. Then hydrogen sulfide appears, marking the entrance into the deep anaerobic layer. The water does not turn into black ink. It darkens because sunlight no longer reaches it. There are no giant toxic bubbles, only an invisible dissolved compound detected by sensors. The sensor frame continues downward for hundreds of meters while the surroundings barely change. That monotony is evidence that deep water is isolated and renewed extremely slowly. Near the bottom, the instrument lights finally reveal fine mud barely disturbed by animals. A remotely operated vehicle advances, sweeping light across a seabed seemingly abandoned by time. From the darkness emerge wooden beams from a ship lost many generations ago. The timber retains its shape because wood-boring and wood-eating organisms cannot survive there. Conditions that exclude animals also transform the seabed into a rare archaeological archive. When deep water bottles return, their contents still look clear and visually ordinary. Only laboratory handling releases the characteristic odor that reveals the hidden chemistry. The journey traveled from blue waves to oxygen-free water without encountering any truly black layer. The name led downward, but science revealed that oxygen, not pigment, was the real secret. The box is not black. It is dark because light cannot enter, and sealed because layers resist mixing. After such expeditions, Black Sea science shifted from exploration toward continuous observation. Automated buoys measure temperature, salinity, and surface oxygen, even when research vessels are absent. Underwater gliders cross the layers and collect data without requiring large crews. Satellites provide wide views of water color, surface temperature, and plankton blooms. Satellite data must be compared with real samples because surface color cannot reveal deep oxygen directly. Computer models connect wind, rivers, heat, and currents to predict where oxygen may decline. These predictions guide vessels toward important sampling areas instead of searching randomly. Along the coast, reducing wastewater and excess nutrients can limit human-driven oxygen loss. River management becomes part of sea management because upstream material eventually reaches the coast. Protecting wetlands also helps trap some nutrients before they enter the sea. Fisheries are tracked alongside temperature and oxygen to explain changing fish movements. When local oxygen loss appears, early warnings can reduce additional fishing pressure. Archaeologists use remote vehicles to film shipwrecks without disturbing protective sediment. Small sediment cores reveal the past without destroying the entire site. Chemical analysis shows how carbon and sulfur interact in oxygen-free water. Studies suggest sulfide can help preserve some organic material in deep water. The Black Sea therefore serves as a natural laboratory for studying ocean deoxygenation worldwide. It shows that a sea can remain blue and biologically active while its depths lack oxygen. A normal surface does not guarantee stability below, so monitoring must continue even during calm periods. The best response is not stirring the seabed, but reducing pressure on the living upper layer. The first misunderstanding is simple. The Black Sea is not permanently black. It can look extremely dark during storms, but any deep sea beneath heavy clouds can do the same. Deep hydrogen sulfide does not dye the entire water black or create a visible ink layer. The rotten egg odor becomes obvious only when deep water is raised and releases gas under suitable conditions. Swimmers near shore do not normally contact sulfide-rich water hundreds of meters below. That does not remove every risk, but it rejects the image of a toxic sea boiling beneath beaches. The deep layer is not completely lifeless. Bacteria and microbes still drive chemical cycles, but it cannot support large fish, marine mammals, or a richly diverse bottom ecosystem. The name also has no single explanation accepted with certainty by every researcher. Darkness, harsh seas, and northern direction are competing theories, not three simultaneous facts. Deep oxygen loss mainly comes from basin shape and stratification, not solely from modern pollution. Pollution remains dangerous because it affects the thin upper layer where most organisms live. The modern turning point is to stop asking whether the sea is black and ask how its layers are changing. Surface color becomes scientific data rather than simple proof of an ancient name. Green water may indicate sediment or plankton, but samples are needed to identify the cause. A beautiful blue surface can still cover a system slowly losing oxygen below. Oxygen sensors therefore matter more than human eyesight when judging the health of the water column. The Black Sea shows that chemical boundaries can matter as much as coastlines drawn on maps. Future management must protect not only surface area, but the volume of water capable of supporting life. That requires monitoring from river basins and coastal zones to the center of the deep basin. No single coastal nation can control water that has crossed many different lands. Marine science must therefore connect data rather than treating each coastline as a separate system. From this new perspective, the deep layer is not only a dead zone, but also a chemical archive. Its sediments preserve traces of climate, rivers, organisms, and human activity. The sea's future depends on protecting the living layer without disturbing the archive beneath. The strongest solution is not changing the name or color, but understanding and protecting every layer. In the afternoon, the Black Sea turns blue again, reflecting white clouds and distant mountains. Below that brightness, the oxygen boundary rests like a door invisible to the eye. Deeper lies the dark box, never truly black, preserving ancient reactions and memories. A geographical name does not always describe color. Sometimes it opens a doorway into science and history.